Last time, how the strange Q cycle creates four protons getting across to the positive side, that's what the little P stands for, from only one QH2. So the last complex, Leninger is showing you that you need to have four cytochrome C. So this molecule up here is one cytochrome C docking. How many electrons does one cytochrome C bring? Just one. No protons, just one electron. So four of them have to come at different times here. And so now you see, I think I warned you about this a long time ago, the stoichiometry here is one oxygen molecule is going to enter in and be reduced to form two waters as opposed to one water, because in the previous slide we were talking about one NADH molecule. So to provide four electrons up here, you need two NADH molecules, a complex one. So we're going to modify the diagram a little bit here. First here we'll point out that copper A here, CuA, is actually two different copper atoms. My guess is that originally the people doing the work only discovered one, and then later, with better techniques, X-ray crystallography, it turns out there's actually two, and they're held so close together by the protein part, subunit 2, that they act as one. So we call that a binuclear site. When two atoms, typically metals, are acting as one. And so the electron wave, or in this case waves, because we have four electrons coming down one at a time, is passing through this first binuclear site on its way to a second binuclear site. So the second binuclear site is right here between a copper atom and an iron in this heme. So these red rectangles here represent hemes. So there's actually a heme here before the second binuclear site. The electron cloud is going through this heme, but it's this one here that the copper and the iron, they're not showing the iron, but the iron's in the center of that heme. They're so close together, they act as one. Is that cool? We're going to see this type of situation in photosynthesis too, where two things come together and act as one. Why, Dr. Hilt, is it doing it this way? No one knows. But it's at this second binuclear site that oxygen is being reduced to water. And so if I was drawing this diagram, I would have this black arrow here. Oxygen can come in from anywhere because it's nonpolar. That oxygen is going to sit right here for a brief millisecond, and right there, not over here, right there is where it gets reduced to water. So being reduced, that's easy to understand because the electrons are coming down from these various cytochrome Cs. But you need protons to make the water. And so the proton is coming from the matrix, which is going to become the negative side because complex 4 is doing two things with protons. It's making water, but it's also pumping protons across to the other side, creating the proton gradient that drives the machine that makes all the ATP. So we've got to modify this diagram here. This general red area is is what we call the D path. So there are two paths that protons hop along. D is the one-letter code of which amino acid? Aspartic acid or aspartate? Yeah, so there is an aspartate in this red region. That's how it got its name. 6 protons are hopping through the D path. So unlike here, let's go back here. Leninger's got 4 protons somehow coming over to here and 4 protons getting across. That's not quite right. So we want to change that. 6 protons are actually going through the D path, so I'm going to get rid of that part. So these 6 protons are hopping through here. By hopping, I mean they're going faster than diffusion. I also mean that a proton up here at the top, a proton coming out, is not the same as the proton coming in down here. Is that clear? So again, that's the same as if this room was a beaker of water and somebody puts a proton right here and a pH electrode way back in the corner. By hopping, the proton gets measured almost instantaneously because the proton that's interacting back there with the pH probe is not the proton over here. Faster than diffusion, almost instantaneous. Pretty cool property of not only water, but weak acid-base groups. So what I would like to suggest that you think about this pathway as a little creek with water flowing through it, and there are stepping stones in the creek. And sometimes the stones are there, and a moment later, they're not. And what the stones are weak acid base groups of residues that are in this path, along with water molecules. Okay? So if I'm walking on that creek, it's a very dynamic creek. But there are things for me as a proton to walk on, so to speak, to be attracted to. The creek is changing because the creek is part of a large complex that is moving. Remember we've said proteins always move? Well, they also move when you send electricity down through the top of it. I mean, you've got an electrical circuit of electrons coming down. They're going to move. They have energy. They can kick in the pants things and make them move. Protein conformation is moving not only from the electrons coming down, but protons, which have positive charges, part of the electrical circuit. You can't just have electrons moving in one direction. You get positives going in the other direction. And so, again, that's where I suggest the creek is a dynamic stepping stone, weak acid base groups moving on and off. It's a little more complicated than that, as we see here. It turns out there's a second path. Why 2 paths, Dr. Hill? We don't know. But there's a second path for protons to hop along. And this is called the K path. K is the 1-letter code for which amino acid? Lysine. So there's a lysine in this pathway. There are other residues that are weak acid base groups, but people who discovered this named it the K path. So 2 protons are going up there. So on our diagram from Leninger, before we started making these alterations, they had 8 protons. 4 get across, and 4 wind up being used to make 2 waters. You've got 2 waters, you need 2 times 2 protons. So we're just saying the reality is it appears to be 6 protons are going this way, and 2 protons dead end right here at where oxygen is chemically transformed into a different molecule, water. Well, if 6 are going this way and 2 are coming up here, and you need 4, not 2, then somehow during this process, 2 must take a right turn on this diagram and get redirected. That's kind of weird, but that's what apparently happened. So right in this region of the complex, turns out that there is an E. E is the 1-letter code of which amino acid? Glutamate, or glutamic acid. And I'm giving you the number just because it's a particular glutamate. Do not memorize the number, but the point is it's a particular glutamate right where there is this turn. And there is a polypeptide chain that comes close to and then far away. So imagine my arm is part of this protein complex, and I'm the glutamate. We talked about this before, when we talked about does a pKa go up or down. This loop comes close to me and then moves away. And the amazing thing is that this segment called the proton gating loop, this is part of the mechanism that's sending some of the protons in the red part over on the right to form water. The pKa of that glutamate changes back and forth from about 4.2 up to 9.4. That's unbelievable. Because remember, pKa's like pH are on a log scale. So that's saying, boy, your ability to grab a proton and then release it dramatically changed. So somehow the E, the glutamate, which is part of the protein, along with residues 169 to 175 that form this loop, together they are directing 2 of the protons from the red channel over to the right to complete the formation of water. Why, Dr. Hill, don't the 4 protons just come up here? I don't have a good answer, other than this whole thing is moving, okay? Now, what complicates the entire process here is that everything is a constant stream in reality. It is not a slide showing 8 protons. So protons are constantly hopping through the red channel and the green one. Electrons are constantly coming down as cytochrome C's bind. Oxygens are constantly coming in. They're nonpolar. They don't have a problem going to the center of this nonpolar complex. And waters are constantly streaming out. Cool? Yes?
So, is the reason that the peak rate changes so dramatically because the glutamate is picking up these protons and then dropping them off?
Well, again, the fact that the pKa changes, let's say it goes up higher, means that's why the proton wants to go onto it. And then when the pKa changes back, that's why it wants to get rid of that proton. So if you want protons to hop along a channel in a certain direction, you have to have some guys who say, come here, proton. Does that make sense? So, very ingenious machine. Yes. Well, again, 2 of them are coming from the D path, and 2 out of the 6 are coming from the red path. So that's where the 4 are coming from. Well, again, the K path is in reality continuous. The D path is continuous too, okay? But when you say, where do the 4 protons come to make 1 water, 2 are coming from the green path and 2 are coming from the red path. But the hopping is so fast, we can't tell out of 6 protons going through the D path, is it the first one and the third one? I mean, it kind of doesn't make much sense to ask the question because it's really a continuous thing. But somehow, 2 of them are going over to the right. Cool? All right, so that's how complex 4 is working. So let's think back to what we talked about last time and now today. We got 4 complexes. Which ones are creating the proton gradient? 1, 3 and 4, okay? 2 is doing so indirectly because the reduced Q is going to complex 3, but it itself is not creating the proton gradient. So we've got all these protons being pumped across the membrane, so long as energy is coming in the form of NADH or succinate. There has to be some energy driving this. And when the protons go across to the other side, they have to be consumed, otherwise it would quickly build up and you cannot push more protons across. You can only create a certain pH gradient. You can't make it infinite. Okay. So now let's use that proton gradient. So that takes us to our other set of slides for today. So there's a machine called the ATP synthase, and it's embedded in the inner membrane. So a lot of things are embedded in the inner membrane. The electron transport chain, succinate dehydrogenase of the Krebs cycle, this machine here. This thing makes ATP in a way that was totally foreign to the people who were working in biochemistry. All the previous pathways that showed the generation of an ATP or a GTP always showed a high energy intermediate. For example, in glycolysis, you would make 1,3-DPG, it had a phosphate on it. You'd make PEP, it had a phosphate on it. You'd expect that the mitochondria must be doing something like that. Turns out it's not that way at all, and so the people who pioneered in this area of research took a lot of grief for a lot of years, because nothing in science gets settled in a year. Many years, lots of different labs confirming that this is the reality. A lot of people got kind of laughed at for coming up with this idea that there's something called the proton motive force that creates ATP. That was unheard of. The machine consists of 2 parts. Well, it has many subunits, but it's considered to have 2 parts. One is called F1, and the other is called FO, not 0, but FO. O stands for oligomycin. It's an antibiotic, and that part is sensitive to binding to this antibiotic. It's a rotor mechanism. So if you think about a Mazda engine, when it first came along with a rotary engine, Cell's have been using this idea for billions of years. It seems new in the car industry, but everything's preceded in life by nature. And then we'll talk about how many protons it takes to make an ATP. So long as the ATP is being made, the protons then are being consumed, and the electron transport chain can continue to pump more protons across. So I want you to see that these things are tied together. You cannot make ATP if there's no proton gradient. Okay, so we're back to this diagram here. And we're going to look at this proton motive force and make some comments. So out here is the cytosol. Here's the outer membrane of the mitochondria. Remember, there are these pores that allow things of 5,000 molecular weight to go in and out from the intermembrane space to the cytosol or vice versa. And so now we've got complexes 1, 2, 3, and 4. And that you can see with one NADH following all those electrons to their final destination, how many protons across from the energy of one molecule of NADH? Look at the diagram, pardon? 10. So that's a lot of protons. So thank you, NADH, you have a lot of energy. You're getting across by different mechanisms, because structures 1 through 4 are different, they function different. But you're getting across 4, 4, and 2, or 10 protons. Now this is creating a positive charge, that's the P part again. And when you move protons across, you leave behind a negative charge. So this is the negative side of the membrane. Protons, being charged, can't cross the membrane unless there's some type of protein to help it. So these protons, being at a high concentration, and hence a low pH, apparently can only get back by going through this machine here, which is the ATP synthase. Sadly, this diagram is wrong in 2 respects. One, the protons do not go up the middle here. They go halfway up, so the proton should be going halfway up here, going around, and then halfway out the other side. And this will become clear in another slide. Are you with me on this? This is very important in the mechanism. The protons do not go up the center. They go halfway onto a merry-go-round that is spinning, and they spin out the other side. The second thing that's wrong is they don't have ATP being made up here at the top of this structure. It's actually being made like about in here, and there's not just one site, there's actually 3 sites. So this thing should have 3 ATPs possibly being made, because there's 3 enzyme active sites. And that'll be clear when we get to this, okay? Future slide. So the proton motive force, really, this part here in the middle, consists of 2 things. One, there's a difference in pH here across the membrane. So there's more protons up here than there is on this side. So that means entropy, delta S, is what's driving the formation of ATP, because this thing is a machine that's being run by protons running through it. So the protons want to get from a high concentration to a low concentration. That's a change in entropy. Remember the Gibbs free energy equation? Delta G equals delta H minus T delta S. So T delta S is a form of energy. The second aspect, this electrical potential, delta psi across the membrane, the protons want to get across to the other side because the other side of the membrane is negative. So there's an electrostatic attraction. So both features are saying to the protons, come on back to the other side. And it's that force, it's like water coming down a river, and that energy is being used to turn a water wheel. So long as the protons are streaming through these machines, the machines can do work. They can create ATP, which is taking some of that energy and trapping some of it, not all of it, because nothing's 100% efficient, trapping some of it in the form of chemical energy, ATP. Cool? Yes? Well, yeah, the succinate dehydrogenase, because succinate enters here, you're getting 6 protons. So succinate, or because it's going to FAD on the enzyme active site, you could say succinate, or its equivalent FAD reduced, gets 6 protons. 6 is still better than 0. Cool? That's a very important question. I'm glad you brought it up. So there are many ways to get the protons across. Remember, I think it was last time we said, hey, that first enzyme in beta oxidation of fatty acids is sending electrons to make coenzyme Q. That would make, anything that makes coenzyme Q docks at complex 3. And so that would generate 6 protons too. So there's a lot of guys creating coenzyme Q that's reduced, creating energy in the form of a proton gradient. So we've got to get across in our mind that having a high concentration of protons on one side of an impermeable membrane is a source of energy. And we're going to see this again in photosynthesis. Turns out most of the energy on the planet is due to proton gradients, not glycolysis. But you can understand how this formation, this way of creating ATP in this very indirect method compared to 1,3-DPG forming ATP is a lot harder to discover in research. This is why historically it came much later. Okay. So, let's focus on this machine. Oh, sorry, this is called the chemiosmotic theory. I'm not sure that that's the best term, but who am I to argue with a Nobel laureate? So Professor Mitchell is the person who first came up with this is the way that ATP is made. He received the Nobel Prize for this. Okay, let's look at this machine. So here is the ATP synthase. And we humans divide it into that F1 and F0 portion. So the Greek letters are F1. So here, for example, this is the part that on the previous slide was sticking out into the matrix. You've really got 3 alpha subunits. So this alpha subunit here is identical to its sister, this alpha, and this one over here. Are you okay with that? And there are 3 betas. This one here, one in the back, one here. So I kind of think of this as, it kind of looks like an orange. Slices of an orange. And right here, I shouldn't have drawn this arrow out here. Right in this crevice between the alpha and the beta subunit is an enzyme active site that can synthesize ATP. So ADP diffuses in, inorganic phosphate diffuses in, and boom, there is right here an enzyme active site. And it transforms that into ATP. So the enzyme active site is at the interface and requires both the alpha and the beta to create it. And since there are 3 of these dimers, that's why there are 3 enzyme active sites in one ATP synthase. Then we have this gamma subunit. The gamma subunit extends all the way up into the interior. It does not bind up here to this delta. And the gamma here is attached to this spinning rotor down here by this protein called epsilon. Okay. So, take your hand for a second. Be graded on this. Curl your fingers together. Leave your index finger like this. But don't make it absolutely straight. Turn it just a little bit so it's crooked. So this down here is not as slender as this. It's actually this hand part down here. Okay? So here's what's happening. This thing is rotating. I can't turn it 360 degrees, but it's going like this. Click, click, click. So apparently this rotor moves 120 degrees at a time. 3 clicks of 120 makes it 360. At the corners of that 120 degrees is one of these dimers. So here's my finger, it's the gamma subunit. When it clicks and kicks that dimer, that energy of forcefully hitting the dimer causes ATP to be released. Because the ATP is being synthesized at the active site of that dimer. But it won't be released until somebody gives it a kick in the pants, changes its conformation so it can't bind to the ATP anymore. Then, the rotor here rotates another 120 degrees, because then it faces the next dimer, kicks it in the pants, releases an ATP, etc. Okay? Go ahead. Well, we'll get to this. What's making this thing move? Okay, first of all, we were doing this. This is fun. We're moving at 120 degrees. Okay. Try doing it in real life. This thing is moving at 6,000 RPM, revolutions per minute. That's pretty fast. You ever had a centrifuge and you set it for 6,000 RPM? That's moving pretty fast. Okay. So we've got this thing zooming around here like this. So the interesting thing is, at least I think, is it can't be straight up, because if it was, it would zoom even faster, but it would never make contact with the 3 dimers. So if it's straight up, that's not good. If it's bent too much, then it gets stuck on one dimer and can't move to the next one, in which case the thing is frozen. So it's this perfect balance between, I gotta hit you, dimers, but not be stuck by you. Cool? Okay. Now, what's causing this thing to rotate? It's this merry-go-round down here. So, FO, meaning oligomycin is sensitive, are subunits A, B, and C. So subunit A is this thing here. It's the one thing that we still don't know very well its structure. We don't know completely, because it's an integral protein. Integral proteins are difficult to get out of the membrane without ruining their structure. The B protein, there's 2 of them here, B2. They're these very elongated proteins. So this guy and its sister, right over here, are extending out of the membrane and holding on to the top of the orange with the delta subunit. So you got this thing, the gamma subunit, rotating. If there wasn't something holding it on the top, the orange slices would just fly away. Okay? Now the C subunits here are the components of this spinning merry-go-round. As it spins, the gamma is attached to this spinning thing. So I'm going to draw one of the C subunits right here. How many C subunits make up this spinning platform depends, as it turns out, on the organism. I'm going to go with 10 because that's what it is in yeast, and that's the best study. But the structure of the spinning wheel would depend on what the proton gradient is across the membrane. If the proton gradient isn't that strong, presumably you need more C subunits. If it's very strong, presumably you don't need as much. The point is, not all mitochondria have the same structural ATP synthase. But let's go with yeast, okay? So I've got one of these C subunits here. And right next to it, these little indentations here kind of indicate, hey, there's a protein. So imagine there's 10 identical of these things, proteins. In the interior here, we assume are lipids, part of the membrane. So this part here the gamma coming down is bound to the top of this spinning wheel. This kind of indicates it goes beneath it. It doesn't. It's bound to the top. Okay, now we see where the protons are coming in. The protons are coming in between the A and the C subunits. So the A subunit it has a channel in it that goes halfway. So I'm a proton here. The proton is hopping through this channel and then jumps onto the C subunit. So let's say this guy right here, the C subunit, has a proton. Well, this rotor's moving, so he continues to hold on to that proton all the way, and its next guy grabs a proton. So in other words, protons are hopping on. So this proton hops on here. It's got to go all the way around, and then when it comes to the back side here in this diagram, it's going to hop out the other half channel. The half channel, again, is made by the A subunit coming up next to the C subunit. So they're making the channel together. Okay, so let's think of it this way. It would be my suggestion. You've got a lot of protons here. This is the positive side. This is the intermembrane space. These protons, let's imagine instead it was water, like a hose. And you put the mouth, the end of the hose right up here, and you turn the pressure on. The water will take the path of least resistance. It will go halfway up, start spinning that rotor, and go shooting out the other side. So the force of the water is driving that paddle wheel, so to speak. Same idea here, only it's protons. Protons are being shot through this thing. They're trying desperately to get to the other side of the membrane. The only way they can actually make it is to go on this weird merry-go-round path and out the other side. I mean, this is so weird compared to glycolysis, right? You can see why it took a lot of years before Nobel Prizes were passed out. One other beautiful thing here, though, and this will be shown on the other slides. When a proton comes on, it's going to go onto a residue in the aspartate that's right here in the C subunit. So there is an aspartate. What's the charge on the aspartate? Negative. I said aspartate, right? So there's a negative charge. So each of these C subunits here, each of one of them has a particular aspartate. So when it comes around to that half channel, it says, come here, proton. The proton comes on, makes the charge 0. And now, because this thing is in a membrane, these are nonpolar tails of fatty acids, phospholipids, that says that the proton can't come off until it gets around to the other side, and now there's water in that aqueous channel. Now it can hop out. So another way of saying this is, you can't have a naked proton with a positive charge go through a membrane unless there's a negative charge